In 1889, the Eiffel Tower became the tallest man-made structure on Earth. Engineers hailed it as proof that modern technology had finally surpassed the ancients. But here's what they didn't tell you. Just 11 years earlier, in 1878, workers tried to restore the dome of Florence Cathedral. They couldn't figure out how Brunelleschi had built it in 1436. The very same engineers who were constructing skyscrapers and suspension bridges couldn't replicate what a 15th-century architect had done with rope and pulleys. And Florence isn't alone. From Egypt to Peru, from India to Mexico, there are structures built before 1880 that modern engineers have tried and failed to reproduce. Not because we lack the technology, but because we can't work out how they did it in the first place. Some of these buildings use construction techniques that defy our understanding of what's possible with hand tools. Others contain astronomical precision that shouldn't exist without computers, and a few demonstrate engineering principles we only discovered in the last 100 years. If you find this fascinating, subscribe now. We explore suppressed history and forgotten technology every week. Don't miss what's coming next. Number 1, the Great Pyramid of Giza. In 2013, a team from Howd in construction attempted to recreate just one block placement from the Great Pyramid using traditional methods, a single block. They had modern cranes, laser levels, and a team of professional stonemasons. It took them 6 weeks to cut, transport, and position 1.25-ton limestone block with the precision found in the actual pyramid. The Great Pyramid contains approximately 2.3 million blocks. Using that same team and timeline, completion would take over 260,000 years. The ancient Egyptians supposedly built it in 20 years. That's one block cut, transported, and placed every 2.5 minutes, non-stop, for 2 decades. But the math gets worse. The blocks aren't just stacked. They're fitted together with joints so tight that a razor blade can't be slid between them. Egyptologist Mark Lehner tried inserting a human hair between the blocks on the pyramid's exterior. It wouldn't fit. Modern stonemasons use mortar because cutting stone to tolerances of less than 1 millimeter is extremely difficult, even with diamond-tipped power saws. The pyramid builders did it with copper chisels and diorite pounders. In 2006, Nova and PBS funded a project to build a small pyramid just 20 feet tall, using only tools available to ancient Egyptians. The team included professional quarrymen, engineers, and archaeologists. They gave up after 3 weeks. They couldn't achieve the precision, couldn't move the blocks efficiently, and couldn't maintain structural integrity for a 20-foot pyramid, not 481 feet. Then there's the internal architecture. The Grand Gallery ascends at exactly 26 degrees. The King's Chamber contains granite blocks weighing up to 80 tons, lifted over 150 feet above ground and positioned with an accuracy of 0.05 mm. Christopher Dunn, a precision engineer with 50 years of experience, analyzed the granite coffer in the King's Chamber. He found evidence of machining marks suggesting tubular drills that could cut through granite at rates of 0.1 inch per revolution. Modern diamond-tip drills cutting granite achieve penetration rates of about 0.02 inch per revolution. Whatever the pyramid builders used was 500 times more efficient than our current technology. Number 2, Baalbek, Lebanon. In the Bekaa Valley of Lebanon sits the ancient city of Baalbek. The Roman Temple of Jupiter stands on a platform made of stones that shouldn't exist. The foundation contains 3 blocks called the trilithon. Each weighs approximately 800 tons, that's 1.6 million pounds per block. In 2014, German archaeologists discovered a 4th block in a nearby quarry. It weighs an estimated 1,650 tons. It was cut, shaped, and partially moved, then abandoned. Modern stationary crane technology tops out at about 20,000 tons, but those cranes require steel construction, hydraulic systems, computer controls, and massive concrete foundations. They also can't move, they lift straight up. The Baalbek stones were transported uphill for a quarter mile and lifted 20 feet onto an existing foundation in the 1st century AD, or possibly earlier. Researchers from the University of Notre Dame attempted to model how the Romans could have moved these blocks using technology described in historical records. Wooden rollers, ropes, and teams of workers. Their calculations showed that moving one 800-ton block would require approximately 40,000 people pulling in perfect synchronization on a wooden track that would collapse under the weight. The model was impossible. They published their findings in the Journal of Roman Archaeology with the conclusion that we don't understand how these stones were moved. But the movement is only half the mystery, the cutting is the other half. The blocks are precisely cut rectangular prisms. The surfaces are flat to within millimeters across spans of 60 feet. The corners are true 90 degrees angles. They fit together without mortar, gaps, or visible seams. Limestone can be cut with bronze tools given enough time and patience, but achieving that level of precision across surfaces that large with that much weight using only hammers and chisels is something modern engineers have repeatedly failed to replicate at any scale. Number 3. The Dome of Florence Cathedral. When Filippo Brunelleschi designed the Dome of Santa Maria del Fiore in 1418, he won the commission by promising to build it without scaffolding or support structures. Every other architect said it was impossible. He was right. They were also right. The dome spans 150 feet. It's built with over 4 million bricks arranged in a herringbone pattern. It's a double shell, an inner dome and an outer dome with a gap between them. The structure supports its own weight through a system of ribs, rings, and carefully calculated brick patterns. Brunelleschi died in 1446 without leaving detailed construction plans. He kept his methods secret to protect his commission. In 1878, during restoration work, engineers tried to understand exactly how the dome stays standing. They built scale models, the models collapsed. They tried mathematical analysis, the numbers didn't work. According to the engineering principles of the time, the dome should have fallen during construction. In 1982, a team from MIT used computer modeling to analyze the dome's structure. They found that Brunelleschi had incorporated architectural principles that wouldn't be formally understood until the 20th century. He somehow understood three-dimensional stress distribution across a masonry shell without calculus, without computer models, and without any documented precedent. Modern attempts to build similar domes using traditional methods have failed. In 2001, a construction company in Italy tried to build a 30-foot replica using period-accurate tools and techniques. They had to abandon the project when the structure began showing stress fractures during construction. The Florence Cathedral dome still stands. We still don't fully understand how, and we certainly can't build another one the way Brunelleschi did. Number 4, Pumapunku, Bolivia. At 12,800 feet above sea level in the Bolivian Altiplano, there's a field of stone blocks that look like they were cut by machines, not primitive machines, modern ones. Pumapunku was built sometime before 1880, with most archaeologists dating it between 500 and 700 AD. The site contains andesite and diorite blocks with flat surfaces, perfect right angles, and complex interlocking joints. Andesite rates between 6 and 7 on the Mohs hardness scale. That's harder than most modern steel files. The builders of Pumapunku, who cut it into blocks weighing up to 130 tons with surface precision measured in fractions of a millimeter. Jesus Escalante, a stonemason from La Paz, attempted to recreate one of the smaller Pumapunku blocks in 2009. He used traditional stone tools and techniques based on archaeological evidence. After 3 months, He had completed about 15% of the block, and the precision was nowhere close to the original. He then tried the same block with modern diamond, tipped power tools. It took him 6 weeks, and he still couldn't achieve the same precision or surface finish. The most disturbing features are the internal right angles and grooves. Some blocks have channels cut into them that make 90 degrees turns inside the stone. The corners of these internal cuts are sharp and precise. Try cutting a perfect 90 degrees internal corner in granite or andesite with any hand tool. You can't. The tool can't reach into the corner to make both surfaces meet at exactly 90 degrees. You need a machine tool like a milling machine that can hold precise angles while cutting. The Puma Punku blocks have dozens of these internal corners. In 2012, engineer Christopher Dunn traveled to Puma Punku with precision measuring equipment. He found evidence of what he calls machine-like precision in the stone surfaces, flat planes that vary by less than 0.02 millimeters across spans of several feet. Modern surface plates, the reference standards used in machine shops to check flatness, are manufactured to tolerances of 0.005 mm. The Puma Punku blocks approach that level of precision in andesite at 12,800 feet above sea level, over 10,000 years ago. Number 5. The Serapeum of Saqqara, Egypt. Beneath the desert at Saqqara lies a series of tunnels containing 24 granite boxes. Each box weighs between 70 and 100 tons. They're cut from single pieces of Aswan granite, one of the hardest stones on Earth. The boxes are so precisely made that the internal corners form perfect right angles. The surfaces are flat to within micrometers, and the lids, weighing up to 30 tons, fit so perfectly that when closed, the seal is nearly airtight. In 2018, engineers from the University of Cairo attempted to analyze how these boxes were manufactured. Using modern laser measurement tools, they found that the internal surfaces of the boxes are flat and parallel to tolerances of less than 0.02 mm. That's precision typically requiring modern machine tools, surface grinders, and precision mills. The ancient Egyptians supposedly made them with copper tools and sand. Several theories have been proposed. Maybe they used tube drills with sand as an abrasive. Maybe they had some kind of advanced copper alloy we haven't discovered. Christopher Dunn tested these theories. He commissioned a machine shop to create a small granite box just 2 feet on each side using any method that could theoretically be accomplished with ancient tools. No power tools, no modern abrasives, just copper, sand, and manual labor. After 6 months and over $50,000 in labor costs, they gave up. They couldn't achieve the precision. They couldn't create the internal corners. And this was a box 1/50th the size of the Serapeum boxes. But here's what really bothers engineers: the boxes are underground. The tunnels are barely wider than the boxes themselves. Some of the boxes are positioned inside chambers where they can't be turned or rotated. That means these 70 to 100-ton precision granite boxes were either carved in place underground in the dark, in spaces where you can barely move, achieving tolerances of 0.02 mm, or they were somehow maneuvered through tunnels with only inches of clearance on each side. Neither explanation makes sense. Number 6. Kailasa Temple, Ellora, India. The Kailasa Temple wasn't built, it was excavated. The entire structure, including the tower, courtyards, galleries, and sculptures, was carved downward out of a single piece of bedrock. The temple is 164 feet long, 108 feet wide, and 100 feet tall. Archaeologists estimate that 400,000 tons of rock were removed to create it. Traditional dating places its creation in the 8th century AD during the reign of King Krishna I. And here's the problem. Modern excavation equipment can remove rock at a rate of about 200 tons per day under ideal conditions. At that rate, removing 400,000 tons would take roughly 200 working days, or about 6 years with modern machinery. The inscriptions and architectural style suggest it was completed within a single reign, which lasted approximately 18 years. But those 18 years include wars, administrative duties, and the construction of multiple other projects. Let's be generous and say they had 10 years of focused work. That's 40,000 tons per year, 110 tons per day, every single day for 10 years with chisels and hammers. And that's just removing rock. It doesn't account for the precision carving, the sculptures, the architectural details, or the fact that you're working from the top down, which means the workers deeper in the excavation are in increasingly confined spaces with limited light. In 1984, archaeologist M.K. Davalekar led a study to determine if the temple could have been built in the time frame claimed. His team concluded that it was technically impossible with the tools available in the 8th century. Modern rock carvers in India attempted to replicate a small section of the temple's carved pillars in 2003. Using traditional tools and techniques, they estimated it would take a single carver approximately 15 years to complete one pillar to the same level of detail. The temple has 34 major pillars, but the real mystery isn't the time, it's the precision. The temple was carved from the top down. One mistake, one miscalculation, and the entire structure would be ruined. There's no way to add material back. You can't fix errors. Architectural historians have found no evidence of major mistakes, repairs, or corrections. Whoever carved this temple understood the exact three-dimensional structure they were creating before they removed the first stone. Number 7, the Parthenon, Athens, Greece. The Parthenon looks like it's made of straight lines and right angles. It's not. Almost nothing in the building is actually straight or perpendicular. The columns lean inward. The horizontal lines curve upward in the middle. The corner columns are slightly thicker than the others and positioned closer together. The spacing between columns varies across the structure. None of this is accidental. It's all designed to correct for optical illusions that would make the building look wrong if it were built with straight lines. This is called entasis and optical refinement. The ancient Greeks understood that the human eye perceives perfectly straight lines as sagging or bending, so they built intentional curves and variations to make the building appear perfect. Here's what bothers modern architects. The Parthenon was built between 447 and 432 BC. The builders had no blueprints in the modern sense, no mathematical calculations we can find, and no way to test their optical theories except by building the actual structure. In 2005, a team of architects attempted to design a replica of the Parthenon using modern CAD software. They wanted to determine the exact curvature rates and mathematical formulas that would create the optical refinements. It took them 2 years and multiple supercomputer simulations to figure out the math. The ancient Greeks did it with string, wooden templates, and visual judgment. But the precision is what's truly remarkable. The curvature of the base is so subtle that it rises only 2.4 inches over a span of 228 feet, a curvature rate of about 0.01%. And it had to be maintained across massive marble blocks, each weighing several tons, positioned by hand. Modern construction can achieve this precision with laser levels and computer-controlled equipment. In the 5th century BC, they used water levels, plumb bobs, and geometry. Teams of stonemasons have attempted to recreate individual Parthenon columns using period-accurate tools. The best attempts take approximately 18 months per column and still don't achieve the same surface finish or optical refinement. The original Parthenon had 40 exterior columns. It was completed in 15 years. Number 8, Roman concrete and the Pantheon. The Pantheon in Rome has the largest unreinforced concrete dome in the world. It has been standing for approximately 900 years. The dome spans 142 feet and contains an oculus, a 27-foot open hole at the top. Modern concrete begins to deteriorate after 50 to 100 years. Highway overpasses built in the 1960s are crumbling and need replacement. The Hoover Dam, completed in 1935, is showing signs of stress and degradation. The Pantheon's concrete is getting stronger. In 2017, researchers from MIT and Harvard analyzed samples of Roman concrete from the Pantheon and several other structures. They discovered that the concrete contains a specific crystalline structure called aluminum tobermorite. This crystal forms through a long-term chemical reaction between the concrete's lime, volcanic ash, and seawater. The reaction takes decades or centuries and actively fills in cracks and strengthens the material over time. Modern concrete doesn't do this. We have tried to replicate Roman concrete formulas for decades. We know the ingredients: volcanic ash from specific regions near Naples, lime, seawater, aggregates of varying sizes. But we can't make it work the same way. In 2013, engineers at the University of California, Berkeley, attempted to create concrete using the exact Roman formula. They matched the ingredients, proportions, and mixing methods based on historical records and chemical analysis. The concrete set and achieved decent strength, but it didn't develop the self-healing crystalline structure. After 5 years of monitoring, their Roman concrete replica was aging like modern concrete, not improving like the ancient version. The problem isn't the ingredients. It's something about the process we don't understand, maybe the specific mixing technique, maybe curing temperature or humidity, maybe some aspect of Roman construction knowledge that was never written down. The Pantheon's dome also uses a principle called aggregate gradation. The concrete at the base contains heavy stone aggregate. As you move toward the top, the aggregate becomes progressively lighter, eventually using pumice and empty clay pots at the crown. This reduces the overall weight while maintaining structural integrity. Modern engineers understand this principle now, but the Romans were using it 900 years ago without the mathematical models or material science we use to calculate proper aggregate distribution. Number 9. The precision stone walls of Cusco and Sacsayhuamán, Peru. In the mountains above Cusco, Peru, there are stone walls made of blocks weighing up to 200 tons, cut with such precision that the joints between them are nearly invisible. The famous 12-angled stone in Cusco has exactly that: 12 angles, 12 separate surfaces that connect perfectly with the surrounding stones. No mortar, no gaps, you can't slide a credit card between the blocks. These walls were built by the Inca, supposedly using stone hammers and bronze tools. Bronze is softer than the andesite and granite they were cutting, like trying to carve steel with aluminum. In 2011, Peruvian stonemasons attempted to recreate a small section of Inca wall using tools and techniques described in historical records: copper chisels, stone hammers, and sand for abrasion. After 6 months, they had completed 3 blocks. The fit was acceptable, but nowhere near the precision of the original. And these were blocks weighing about 2 tons each, not 200 tons, but the real mystery isn't just the cutting. It's how the blocks were moved and fitted together. Some of the Sacsayhuamán blocks have knobs and protrusions on their surfaces. For decades, archaeologists assumed these were decorative. Recent analysis suggests they may have been used in the moving process, but no one can figure out how. Several blocks were quarried over 20 miles away and transported across mountain terrain with elevation changes of thousands of feet. A 200-ton block on a wooden sled would sink into any surface, even solid rock, under its own weight. Rolling it on logs would crush the logs. Modern heavy transport uses hydraulic trailers with dozens of wheels, distributed weight, bearing, and powerful diesel engines. Moving a 200-ton load requires careful route planning, road reinforcement, and engineering analysis. The Inca did it on mountain paths, but here's what really bothers experts: the blocks aren't just fitted together on flat surfaces. They're fitted in 3 dimensions with complex curves and irregular shapes that lock together like 3D puzzle pieces. In 2015, structural engineers from Japan analyzed the Sacsayhuaman walls using 3D scanning technology. They found that the walls are designed to withstand earthquakes through a technique called seismic dampening. When an earthquake hits, the stones shift slightly, absorb the energy, and then return to their original positions. The precision fit allows micro movements without the wall collapsing. Modern earthquake-resistant construction uses similar principles but with steel reinforcement, shock absorbers, and flexible joints. The Inca achieved it with nothing but precisely cut stone. Number 10, Göbekli Tepe, Turkey. In 1994, archaeologists began excavating a site in southeastern Turkey that shouldn't exist. Göbekli Tepe contains massive stone circles made of T-shaped pillars, some weighing up to 20 tons, decorated with intricate carvings of animals and geometric patterns. The site is approximately 11,500 years old. That's 6,500 years before Stonehenge, 6,000 years before the pyramids. It was built before pottery, before metal tools, before writing, and before agriculture. According to the standard archaeological timeline, the people who built Göbekli Tepe were hunter-gatherers. They didn't have permanent settlements, complex social structures, or specialized labor forces. Yet they quarried, carved, transported, and erected stones weighing 20 tons, organized them into complex circular structures, and decorated them with sophisticated artistic reliefs. In 2018, archaeologists attempted to move a replica T-shaped pillar weighing 10 tons, half the weight of the largest Göbekli Tepe stones, using only tools available 11,500 years ago, wooden sledges, rope, and human muscle power. It took 150 people to move the stone across flat ground for 100 meters. The sledge broke twice, the rope snapped repeatedly, and this was on level terrain, not up the hillside where Göbekli Tepe sits. The site contains approximately 200 pillars across multiple circular structures. Some are still buried. If each pillar required 150 people for transport alone, not including quarrying or carving, the labor force needed would rival early civilizations, not small bands of hunter-gatherers. But the construction is only part of the mystery. The carvings on the pillars show animals that are anatomically accurate and artistically sophisticated. Foxes, lions, wild boars, snakes, scorpions, and birds, all rendered in high relief with attention to detail that suggests the artists had deep knowledge of animal anatomy and behavior. Some pillars contain geometric patterns and symbols that may represent early writing or astronomical notation. But we don't know they predate any writing system we've discovered by thousands of years. In 2003, a team of engineers analyzed the quarrying techniques used at Göbekli Tepe. The pillars were cut directly from bedrock using percussion tools. The quarry sites show evidence of controlled fracturing, where large sections of limestone were separated from the parent rock using wedges and hammers. This technique requires understanding of stone grain, fracture mechanics, and stress distribution. Modern quarries use hydraulic splitters and diamond wire saws. At Göbekli Tepe, they did it with stone hammers. The precision of the pillar shaping is equally puzzling. The T-shapes are symmetrical, the surfaces are relatively smooth, the reliefs are carved to consistent depths. Experimental archaeologists have attempted to replicate Göbekli Tepe pillar carving using flint tools and stone hammers. Their estimates suggest each pillar would require approximately 500 hours of skilled labor for shaping and carving. 200 pillars times 500 hours equals 100 hours of specialized stone carving for a society that supposedly didn't have specialized craftsmen. And here's the final mystery. After all that work, after investing potentially decades or centuries into building these massive stone circles, someone deliberately buried the entire site. The structures were carefully filled in with debris and soil. They weren't destroyed or abandoned. They were buried intact, preserved underground for 11,500 years. Why would you build something so massive, so precise, and so labor-intensive only to bury it? We don't know.
We know how old it is, we know approximately how it was built, but we don't know why it was built, who built it, or why they buried it. Modern construction companies with excavators, cranes, and power tools couldn't replicate Göbekli Tepe using Stone Age technology. Multiple teams have tried, all have failed. 10 structures, 10 different locations, 10 different time periods, one common thread. Modern engineers, with all our technology, education, and resources, cannot figure out how ancient builders accomplished these feats, not because the structures are impossible. They exist. We can see them. We can measure them. But we can't replicate them. We build skyscrapers that sway in the wind. They built stone temples that survive earthquakes for thousands of years. We create concrete that crumbles in decades. They created concrete that strengthens over centuries. We need computer models to design optical refinements. They did it with string and judgment. Either ancient builders possessed knowledge and techniques that were lost, or our understanding of technological progression is fundamentally wrong. The standard narrative says technology progresses linearly. Simple tools lead to complex tools. Primitive techniques evolve into advanced techniques. Each generation builds on the knowledge of the previous one, but these structures suggest something different. They suggest that at multiple points in history, in multiple locations around the world, builders possessed capabilities that exceeded what their supposed technology should have allowed. Some researchers propose that advanced knowledge existed in the ancient world and was lost through catastrophe, war, or the collapse of civilizations. Others suggest that our dating methods are wrong and these structures are far older or younger than we think. A third group argues that ancient builders simply had more time, more patience, and more skill than we give them credit for, that given enough human effort and ingenuity, the impossible becomes possible. Maybe they're all partially right. What we know for certain is this: these structures exist. They were built before 1880, most of them long before, and despite all our modern technology, we cannot reproduce them using the methods that supposedly created them. That should tell us something about the limitations of our knowledge and the hubris of assuming we understand everything about the past. If you want to explore more suppressed history and lost technology, check out the video on screen now and subscribe so you don't miss what we uncover next. I'll see you in the next one.